Hi guys, welcome back to another video of me teaching, and today I have this question on the board for you guys. So why don't we just get into the question? Well, this question looks weird, right? But I think that you guys will think that this is super easy because isn't P of m just you plugging m to here and it becomes m over 1 plus m? Well, if you thought that, sadly you are wrong. Why? Because this p of x isn't even a polynomial. It's just a rational function. This just gives us a pair x and px. It doesn't actually do anything. Now we see that there are n plus 1 values of k, and p of x is of degree n. And we can theoretically figure out p of x, then plug in m, and that works for a degree 2 polynomial. It's pretty simple. But for this degree n polynomial, no, that is way too hard. Another way is using something called the Lagrange interpolation. Now, that is a university method, so I'll put that aside. And for today, I'm just going to use a high school method. But what do we do? Well, what I'm going to do is I'm going to construct a new polynomial called h of x. Now, what attributes do I want this h of x to have? Well, I want this h of x to involve p of x, right? Because we want to find p of m, and we can't just make a random polynomial, right? So I want this to involve p of x. Secondly, I want all these values of k to be the roots of this polynomial. So how do we construct it? Well, if we notice, when these values are equal to k or 0 to n, then p of k transforms into this. Now, to make these roots of h of x, then we want this polynomial, if we plug in these values, to be equal to 0, right? And we can take advantage of p of k being this, because all we have to do is make 1 plus x times p of x. Now, why do we do this? To cancel out the denominator, but we still have the numerator left, right? So we subtract the numerator. Well, this works because when x is k, or k is 0 to n, then p of k is this, and these all cancel out to make it 0. So this is equal to 0 when x is k, or 0 to n, right? And we see that h of x is of degree n plus 1. Why? Because p of x degree n, and this is an extra degree 1, so that's degree n plus 1. And we have exactly n plus 1 roots. So that means when we factorize this, which we'll do now, there won't be any leftovers. So it's x. So when we factorize it, it's x minus 0 times x minus 1 all the way until x minus n. Is this it? No, because we still need to multiply by a constant c. So then the real question is, what is c? Well, we need to plug in some sort of initial value, right, for x. Well, what initial value should we plug in? Well, if we do a little bit of thinking, we can see that h of negative 1 will be the ideal value. Why? Because when we plug in negative 1, this first term is 0, so we don't have to deal with any of this p of x stuff. So h of negative 1 is just 1, because negative 1 is 1. And also, if we plug in negative 1 to this, then we'll see it is c times negative 1 times negative 1 minus 1, all the way to negative 1 minus n. Okay, now we see there are so many negatives, and we don't like that. We like positives. So I want to take out all the negative ones. Well, how many brackets are there? N plus 1. So it is negative 1 to the power of n plus 1, then multiply by, this becomes 1, this becomes 2, and all the way multiply until n plus 1. And that is the definition of factorial. So we just multiply by n plus 1 factorial. So now we can find that c is equal to, we can just divide this here, 1 over negative 1 to the n plus 1, multiplied by n plus 1 factorial, right? And also, if you use your brain, then we see that 1 over negative 1 to some power is the same as just this. So it's the same as this multiplied by 1 over n plus 1 factorial. And you can double check this on your own. So now that we have c, then we can plug this back into here. And I'm just going to rub this out. This is equal to, c is this. And then we have to multiply by this. Right. So I can rub this out. Now we see that this h of x is equal to this. Okay, now what do we do? Well, first of all, we see that h of x is this, right? And we want to figure out p of n, right? So the first step I'm going to do is I'm going to replace this with just this, right? Because h of x is this and is equal to this. Okay, and now I'm going to plug in for x equals to m. So 1 plus m, p of m minus m is equal to negative 1 to the n plus 1 times 1 over n plus 1 factorial, then multiplied by m times x minus, m times m minus 1 all the way until m minus n, right? And now I'm going to simplify this a bit further. So long fraction, okay, m factorial, because this is m factorial, because m factorial is m multiplied all the way down to 1. But this only goes down to m minus n. Well, what can we do? Well, we can divide this by m minus n minus 1 factorial. And of course, don't forget about this fraction times n plus 1 factorial. Now, if we notice something, this is just cm n plus 1, right? m factorial over the bottom factorial, which is n plus 1 factorial, and then multiplied the top minus the bottom factorial. So this is equal to negative 1 n plus 1 times c m n plus 1, right? So now we can figure out p of m, but I'll just rub this out and I'll leave this. Okay, so now that we have this, I can move this m just like that. And then I'm going to divide the 1 plus m. So p of m is equal to this over 1 plus m. Now we see that this is very different from just m over 1 plus m, right? Well, it's sort of similar because we have m over 1 plus m here, but we have this extra stuff. So this is the final answer to this very interesting problem. So thank you guys so much for watching, and if you enjoyed my video and you want more videos like this, please consider liking and subscribing. If you want to master something, teach it.